Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
In lecture yesterday, I said a few words about this second phase of the argument where you have to justify Ricci flow with surgery and show that the process can be continued for all time. And so actually, if you think about the nature of the surgery process, then if you look at some time t, it's not a surgery time, then you can recover the original manifold by taking the disjoint union of the manifold at time t, this m sub t, with a collection of spherical space forms, and then you perform a bunch of zero surgeries on that. Now, what's a zero surgery? An example would be a connected sum. Okay, the only thing that's more general than that is kind of a self-connected sum, where you have something which is connected, and you scoop out balls from the same component and glue them. Okay, so that's what that means. So, I mean, this just follows from the nature of the surgery process. Remember, you're cutting out, when you cut along the spheres, you understand the topology of the stuff that you threw away. And there are also some components which you might throw away because the entire component becomes singular. And those the topology of those guys is also understood and can be, and those pieces can be constructed this way. Okay? So, yeah, so one possibility that can occur here is that from some time t onward, the manifold is actually empty, okay, because you threw away your last connected component. In that case, you say that extinction has occurred. So the Ricci flow surgery has become extinct. Now, this is actually a favorable case when extinction is a good thing, because in that case, the original manifold can be obtained from a collection of spherical space forms by performing zero surgeries. Okay, so and that implies that when extinction occurs, the manifold satisfies the geometrization conjecture. Right. So this is a case where you have kind of early termination of the proof. Now, what are some situations where you can guarantee that the flow with surgery will become extinct? So the simplest case to think about is the case when you have a metric which has everywhere positive scalar curvature. Okay, so if you have either a metric which either initially or from some time, at some moment has positive scalar curvature, then you look at the evolution equation for the scalar curvature. This is a slightly different way of writing it than I had before. So here, what you see is that, I mean, so this term is positive, non-negative here, so you throw it away, and you apply the maximum principle to the minimum value of the mean curvature, and you get this differential inequality for the minimum value of the mean curvature. Okay, and if you remember from last time you taught ODEs, this ODE blows up in finite time. Okay, when you have power 2 sitting there. So that forces the minimum value of the scalar curvature to go to infinity in finite time, which means the manifold must actually be empty from that time onward, because if you had a single point in the manifold, that would provide the scalar curvature would provide a finite upper bound for the minimum, right? Okay, so if the scalar curvature is positive, then you get extinction. In fact, if the scalar curvature is non-negative, well, you don't necessarily get extinction, but the borderline case of this analysis would tell you that the scalar curvature would have to be dead zero, and this term here, which is non-negative, would also have to be dead zero, which forces the manifold to be dead flat. And in that case, one also understands the topology of the manifold. So either of these two cases are cases where the geometrization conjecture holds. So in particular, so one can if you like, you can imagine modifying the surgery process. After you perform the surgery, if you end up with a connected component, which either has non-negative scalar curvature or admits some metric with non-negative scalar curvature, you can just throw that away because it satisfies the geometrization conjecture. Okay. Now, another extinction result, which is very nice if you're interested primarily in the case of the Poincare conjecture, or the case of three manifolds with finite fundamental group, is the following. So it says that if your initial manifold has no aspherical summands in its prime decomposition, well, then extinction occurs. All right. So aspherical just means the universal cover is contractible. So an example of this would be just take a bunch of spherical space forms and take their connected sum. All right. But anyway, if you take the original manifold, you do the prime decomposition, right? And you look at the piece. If it's not aspherical, then geometrization holds for it, just because the Ricci flow surgery will become extinct. So I don't say anything about this Kolding-Minkowski or Perelman argument. So apart from saying that the idea is that, so there's a calculation that goes back to Hamilton, which says that if you have, this is a slightly different case, but the idea is that if you have a minimal two-sphere sitting in the time slice at some time, okay, and then you know, of course, the metric is changing with time. Okay, so if you calculate the time rate of change of the area of that minimal surface, there's a formula which tells you that its area will be decaying. The time derivative of the area will be negative, and it will be bounded above by some function of the area itself. And so this differential inequality would imply that if you had, as your flow evolves, if you have a family of say, minimal least area two spheres, least area in some sense, then the area has to decay to zero in finite time. Okay? So in particular, this implies that the manifold has to become prime from some time onward. Because, if not, you would simply look at each time, you would consider the class of embedded two spheres, which are non-trivial. Topological, they don't bound a three ball. And you look at the one with least area, okay, and you take its area. So that you can show that the area of that least area sphere would decay to zero in a controlled way, and so therefore from some point onward such two-sphere can exist. Now the idea of Kolding and Minkowski is to work instead of with least area spheres, they work with minimax two spheres, and employ essentially the same calculation. Okay.
It's not important that the minimax be embedded.
No, it's not. Yeah. There's no good way to construct embedded minimax, as I imagine you know well. Okay, so let's now think about the case that extinction does not occur. All right, so we know in particular that we can assume that the minimum of the scalar curvature is strictly negative. Okay, let's bear that in mind. And so what we would like to do is to see that that as time goes to infinity, we can recognize that the manifold at time t is actually a collection of hyperbolic manifolds glued along incompressible tori to graph manifolds. Now remember, this was this assertion was one of the assertions that, an equivalent way of stating the geometrization conjecture. Okay, so I had it up there before. All right, so this is what I want to try to discuss today.
Let me just ask, the graph manifold collapses to something lower dimensional, but does that take finite or infinite time?
Well, Okay, speaking loosely takes, yeah, infinite time.
Except for some cases, like the length space is a graph manifold.
Yeah, I mean, I would be a little bit hesitant to say that the graph manifold collapses, because, I mean, at this stage, you don't even have a clearly identified portion of the manifold in view. I think it'll come out. It'll come out in the course of the discussion here.
Is there a canonical graph manifold by taking the complement of the hyperbolizable pieces?
It's topologically canonical, yeah, but then as soon as you use the word collapsing, that implies that you're looking at a something with a metric on it. So in particular, you've identified a particular subset of the manifold with its metric in order to talk about collapsing. So I haven't gotten to the point where I've identified a subset yet. Okay, so this, roughly speaking, the way this is going to come out, so again, you see a kind of decomposition of the manifold into two pieces. Before we saw it with the kind of the thick part, and then these tubes, the necks, and cap necks, and so on. There'll be a similar decomposition here, speaking very crudely. But where the thin part has a different structure. It's not analyzed by using kappa solutions. It's analyzed using a different technique. Okay. But anyway, we'll have some kind of thick, thin decomposition here. So what we're going to do is we're going to be looking at time slices for large T, and we want to look at those at scales at most comparable to the square root of time. Okay. This turns out to be the natural scale to consider. So, in particular, if you take something like a hyperbolic manifold, okay, right, and you let that evolve for time t, then the diameter will be like root t. Okay, so you'd want to scale back by root t. All right, so the thick part I'll denote by m plus. So the point is it belongs to the thick part at time t if there's a scale comparable to root t such that the parabolic ball centered at this point, xt, radius r, has controlled normalized geometry. Okay, so what do I mean by controlled normalized geometry? So if you have a ball in a Riemannian manifold, say an R ball, then I'll define the normalized ball to be the Riemannian manifold you get by rescaling to make the radius equal to 1. Okay? So that's the normalized ball. And so if I look at the original ball and I speak of, say, the normalized curvature, what I really mean is you look at the normalized ball and you look at its curvature. So it's just defining the scale invariant quantity by normalization here. So when I say that the parabolic ball has controlled normalized geometry, I'm meaning you rescale it so that the radius becomes 1. And then after scaling, there'll be upper and lower bounds on the curvature, and also there'll be a lower bound on the injectivity radius at the base point. Okay, so that's what I mean here. So the thick part, this is beginning to pick out this sort of a first approximation to this decomposition to the hyperbolic part and the graph manifold part. Okay, so we're going to get there by successive approximations. Now, what's the thin part? So a point belongs to the thin part if there's some scale less than root t, such that if you look at the ball, now this is not a parabolic ball, it's just a ball in a time slice. It's a ball which has normalized curvature at least -1 and small normalized volume. Okay? So there's some radius which might be very, very small with the property that when you rescale this guy to have unit size, you get something which has a sectional curvature at least -1. There's no statement about an upper curvature bound. Just the sectional curvature should be at least -1. And the volume now of this rescaled ball is small. Okay? So an example you could think of would be something that looks locally like a flat R2 across a short circle. Okay? So an example of this would be something that's collapsed in the sense that we were discussing before. Okay. So let me give this a more precise version of this kind of thick-thin decomposition. Probably shouldn't be calling it thick-thin decomposition. But anyway, so for all w bigger than 0, this is the measure of the kind of collapsing here. So there are numbers lambda and k, so that if you have a point in the manifold at time t, one of the following two alternatives occurs. So either the parabolic ball centered at this point of scale lambda root t. So again, lambda is bounded away from 0. So this is, parabolic ball has radius comparable to root t, you should think. This has normalized curvature at most k, and the normalized volume of each of its time slices is at least half the volume of the Euclidean unit ball. Okay, so we have a parabolic ball, which is this ball in space-time, and the time slices are just these horizontal parts of it. And the other case is, well, we saw before this, in R less than root t, so that this normalized ball has sectional curvature at least -1 and volume at most w. Okay, so with this parameter w, we can define these two subsets of the slice at time t. So there's m plus at w at time t, okay, and then m minus w comma t. Right? So one thing you want to notice here is that if m plus wt is non-empty, well then that means that the volume of the slice at time t is bigger than a constant times t to the 3/2. See, that's because if m plus is non-empty, you have a point of the type up there, right? So its radius is comparable to root t. Okay, you have bound on normalized curvature, and so and bounds on injectivity radius. So inside the ball bxt lambda root t, there will be a ball which is by Lipschitz to a Euclidean ball of radius lambda root t, with controlled by Lipschitz constant. Okay, so all I'm saying is that if you just look at the top of this parabolic ball, so the corresponding ball in the final time slice, that already contributes volume comparable to t to the 3/2. Okay. Okay, so this brings us to collapse with the lower curvature bound. So the assertion here is there's some threshold number, W0, such that if your time slice, MT, has no thick part. Okay, so it consists entirely of these, this set M minus. Well then, well, I mean, if it's equal to the M minus, more precisely, well then, this is a graph manifold. Okay, so more generally, you can say that even if M minus is not the entire manifold, okay, roughly speaking, you can say that part of the manifold is a graph manifold. It's not quite true. You have to be a bit careful about what's happening near the boundary. But so to say this correctly, but vaguely, you can add a collar to this in a geometrically defined way, so that you get a graph manifold. Right? So I want to say a little bit about how this works. Right? And it's based on the theory of collapsing, or a local version of that, with a lower curvature bound. And this is carried out in work by Shuei and Yamaguchi. And their work doesn't, I mean, there's one special case that comes up when you want to apply that here. And that special case is not quite covered by Shioya and Yamaguchi, but if you feed in some extra information coming from the fact that you have a Ricci flow, then you can do it. Okay? So I want to say something about this collapsing theory. So so this collapsing with a lower curvature bound, so what is this? A simple case would be you have a sequence of Riemannian manifolds, say Riemannian 3 manifolds, with sectional curvature bounded below by -1, okay, where the volume goes to 0. All right. So since the volume is going to 0, this is certainly not going to be converging in any natural sense to a three-dimensional Riemannian manifold. It's degenerating. Okay. Now, so the theorem says in particular that that if you have such a sequence of manifolds, then for sufficiently large, I mean, except for finitely many guys in the sequence, they will be homeomorphic to graph manifolds. Okay. So so let me put this into some context. So the earlier version of collapsing theory is Cheeger-Gromov collapsing theory. And that's a situation analogous to this, except where you take a sequence of Riemannian manifolds where you'd have both a lower bound, say -1, and an upper bound on the curvature. So you have two-sided bounds on the curvature, and you say the volume is going to 0. Okay? And so the Cheeger-Gromov collapsing theory is, well, I mean, the basic ingredient that goes into this is well, the Margulis lemma and the geometry associated with this. It says that if you have bounds on curvature and you have a point with small injectivity radius, okay, so then near that point, the manifold has very restricted geometry. Okay, so the examples that we've come up with, seen so far, would be something like a flat cylinder. Okay, with small, where you take a real line, cross a circle with small diameter, or the real line cross a torus, or maybe a torus. There are more general examples, so you can have a three-dimensional nil manifold, okay, of the same sort. So but essentially the Cheeger-Gromov theory is based on this so-called Margulis lemma. Now, when you drop, if you go back to the situation where you have a sequence of Riemannian manifolds where there's just a lower bound on sectional curvature, okay, and you assume the volume is going to 0, then the methods for proving that the manifolds that these guys are eventually graph manifolds are completely different. Okay, so the method for proving it is to kind of argue in two steps. So you have the sequence of Riemannian manifolds with lower curvature bound. So the first thing you do is to pass to a weak limit. You know it's not going to converge in a smooth topology to a Riemannian manifold. However, it's fairly elementary to see that it has a Gromov-Hausdorff limit. Okay, so you can take I mean, at least if you select a sequence of base points, it will have a Gromov-Hausdorff limit. And that Gromov-Hausdorff limit, it's not a Riemannian manifold, but it's an Alexandrov space with curvature at least -1. So this is some class of metric spaces that was introduced a long time ago and was developed quite substantially starting in the end of the 80s, in the 90s, by, well, among other people, Perelman himself. Okay, so you get this sequence of manifolds, and it converges in this kind of weak topology to an Alexandrov space. And it turns out, under these circumstances, the Alexandrov space has to have dimension 0, 1, or 2. And the zero-dimensional case is not very interesting. Okay, but so if it's one-dimensional, it could be just a circle or an interval. If it's two-dimensional, then topological.
You mean topological dimension, or what?
Well, in this case, it turns out that topological dimension and the Hausdorff dimension will coincide. So most reasonable notions of dimension agree.
Give us a definition of Alexandrov space.
Yeah. So so if you have, let's say you have a metric space Z, so it's a geodesic metric space. Okay, so then, so any 2 points in there are joined by a geodesic whose length, is equal to the distance between the points. So, if you want to define let's say that this has curvature bigger than or equal to -1, we draw over here, we take a copy of the hyperbolic plane, which has curvature equal to -1. everywhere. And this should, the geodesic triangles in this space Z are supposed to satisfy a triangle comparison inequality, which is just the following. So if you have, if you have a geodesic triangle with side lengths A, B, and C in Z, then you can construct in the hyperbolic plane a geodesic triangle with the same side lengths. Okay? And the assertion is that if you look, for instance, so here's a vertex A, big A, opposite to the side little a, it says that if you choose a point on this side, let's call this X, and you construct the corresponding point over here, so this distance here is equal to that distance, and this is the same as that. Well, then the distance here, let's call this L. And over here, say L bar. So then L should be bigger than or equal to L bar. Okay, so that means that the geodesics are at least as geodesic triangles are at least as fat as the geodesic triangles in hyperbolic space. Right. So this property is preserved. Under these limiting operations. So if you start with the Riemannian manifold with sectional curvature at least -1, that's an example of an Alexandrov space of curvature at least -1. Then you pass to this weak limit. That will be a geodesic metric space, which is an Alexandrov space with curvature at least -1. Okay, and these spaces have reasonably nice structure. So to get some idea of the regularity, you might just think of an arbitrary convex body sitting in R3, okay, with non-empty interior. Just look at the boundary of that, the frontier, and the induced path metric on that. Okay, so that's an example of an Alexandrov space with curvature bigger than or equal to 0. But you can have cone points and so on. So the idea is that
Alexandrov spaces can also have topological singular points. So, for instance, does any simplicial complex have a metric making it an Alexandrov space?
Not with lower curvature bound. So it's actually the topology is fairly restricted. So I mean.
I see what you're saying.
So there's another notion whether you have an upper curvature bound and any polyhedron has a metric with curvature bounded above by 1, for example. But
for example, just a tree, a cone on 3 points would have infinite curvature.
Right.
Okay.
Okay. So we know. Let's come back to our sequence of Riemannian manifolds with curvature bigger than or equal to -1. It has this. I'm sorry. I haven't gotten to it yet. So, yeah, so the idea is we have this limit of, if we take this Grove-Hausdorff limit, that's this Alexandrov space. An interesting case to think of is when the limit is two-dimensional. And you get something which is, it's a metric space, it's a geodesic metric space, curvature, that's an Alexandrov space of curvature at least -1, but topologically it is a surface with boundary. Okay, so topologically it's not that bad, and one can describe the geometry pretty well. I think this example of a boundary of a convex body gives you a pretty good idea what the geometry, the range of possibilities is. You can have cone points, but you can't have, you can have only finitely many cone points whose cone angle has a deficit from 2 pi, a given deficit, at least a given deficit from 2 pi, at least in a compact piece. And so it turns out that if you look at how this sequence of Riemannian manifolds converges to this limiting Alexandrov space, then away from a controlled number of cone points, okay, the Alexandrov space looks up to small bi-Lipschitz constant, looks almost Euclidean. Okay, so open these cone points, you have a nearly Euclidean part of the limit space, and it turns out that if you have a sequence of Riemannian manifolds converging to something Euclidean or something nearly Euclidean, then this convergence implies a local fibration structure on the approximating Riemannian manifold. Okay, so in this case it would be producing a circle fibration. All right, so this kind of degeneration produces local fibration structure. Now you have to study what happens near the cone points. I mean, it's a generation near the cone points using a somewhat different argument, but it's a similar flavor. And this eventually builds a bunch of different fibrations on the three manifolds you started with, and you have to glue them together. But this yields the graph manifold structure. Okay.
So should we think of any fiber as the set of points collapsing to a specific point in the limit?
Yeah, morally speaking, yeah. I mean, the point is that you can produce using distance functions, transferring distance functions from the limit. I mean, you can use distance functions from appropriately chosen points to define kind of an attempt at a coordinate system on the Alexandrov space, and you can transfer those distance functions up to the Riemannian manifold. So it actually produces a map to R2, which you shows behaves topologically like a submersion, and that gives you the fibration.
Mm-hmm. So it's locally by Lipschitz equivalent to that picture?
It's locally
by Lipschitz equivalent to that picture?
Yeah, at least in the Alexandrov space. I mean, in the base. Okay. All right. I mean, this is all very impressionistic, but I'm just trying to give you an idea of the ingredients that go into this. So Perelman's stability theorem it comes in when you're trying to analyze what happens near the cone points, and its stability theorem says that if you have a sequence of Riemannian manifolds which converge to, Gromov-Hausdorff converge to an Alexandrov space of the same dimension, all right, then all the manifolds sufficiently far out in the sequence are homomorphic to one another. Okay, so this is, I don't want to say too much more about this, but this is these are the ingredients that go into understanding the geometry of M minus. Okay, so for the rest of this, I'm going to be focusing on this M plus, the part where the part where you have the parabolic ball of size comparable to root T, which has controlled normalized geometry. Okay, controlled curvature, controlled injectivity radius. Okay, so should we break here for 5 minutes? So we'll start at 2:20 then.
Is that stability theorem true in every dimension, by the way?
Yeah, as I